I think we have now reached our last problem. Let's do a time check. I need 6 more minutes, and boy, I have 6 minutes. It's perfect. 1E3 deals with a geosynchronous satellite. Let's first consider a circular motion, radius r, and there is an object going around with a constant speed. Speed for me is v. Here the speed is the same, that is v. But be careful. The velocity vector here is different from the velocity vector there, because the direction has changed. The magnitude, which we call speed, this is speed, that is only the magnitude of the vector. But the direction of the vector is very important, and the direction changes, and so since the direction changes, there has to be an acceleration. Otherwise the vector v could not possibly change. In this situation, which I will give you without proof, the acceleration is always pointed towards the center. That's why we call it centripetal acceleration. It's therefore also changing. A itself is not constant, and v is not constant. A is pointing in this direction, and A is pointing here. A is constant. The magnitude of the acceleration is constant. And that, I will give you without proof, is v squared divided by r. And sometimes you see a little c here, which indicates centripetal. It's pointing towards the center of the circle. Now you can take an apple and swirl an apple above your head in more or less a horizontal plane. If you can do that at constant speed, then you have a situation like this. A car which going around in a circle, if the speed of the car were not changing, you would have a situation like this. Take a satellite going around the Earth, putting it in a circular orbit, you will have a situation like this. Take a planet around the Sun, put it in a circular orbit, you will have a situation like this. And in your particular case, you're being asked to calculate the centripetal acceleration for a geosynchronous orbit. A geosynchronous orbit is an orbit whereby the satellite takes 24 hours to go around the Earth. And if you launch that satellite in the plane of the equator, then, and you should think about that, when you look from any point of Earth at that satellite, it will not move relative to the rotating Earth. Because the Earth rotates in 24 hours, and the satellite rotates in 24 hours, so the satellite will appear to stand still in the sky relative to the Earth. Of course, not relative to the stars. It has to be launched in the equatorial plane. You think about that. That's a must. Otherwise, it does not stand still in the sky. Well, the orbital period is 24 hours. And the radius of that orbit was given to you. There will be a time that you can calculate that if you have Newton's laws and Kepler's laws. So the velocity will be 2 pi r divided by 24 times 36 hundredths. That would be in kilometers per second. And so the centripetal acceleration, which is v squared divided by r, I think I found something like 0.2 meters per second square, but you better check that.